SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 24. This is going to be a little bigger module time wise, because we are wanting to complete some of the leftover distributions like Poisson's distribution or normal distribution, and how you can derive all those different distributions with respect to the acceptance sampling plan and binomial distribution that you have just done in the last few modules. So let us first start with the task leftover of representing or calculating the expectation or the mean value of the binomial distribution. And because, as we said, that it is a discretized distribution in x, so basically sigma x varying between 1 and n x px, where x is basically the number of defectives and px is exactly the probability of those number of defectives and a certain amount of draw size or sample size, okay, as you saw in the last example of good versus defective. Okay. So in the same manner we are going to calculate the mathematical expectation or the mean and the standard deviation of such a distribution. So let us say we designate R as the number of rejectable items found in a sample of size n, that is p fraction rejectable. Okay, so this is exactly the percentage defective which is there in the sample, so we call it fraction rejectable. The expectation of R is given as ER sigma r varying between 0 and n r times of NCR p to the power of r 1 minus p to the power of n minus r, where sigma r varying between 0 and n NCR p to the power of r 1 minus p to the power of n minus r is actually equal to 1. Okay. So we want to find out the expectation of this particular distribution. So we are basically multiplying it by exactly the probability of r rejectables in a sample size of n, and multiplying that by r just because it is discretized x px. So this is the p of r, and we are multiplying that by r, and r varies between 0 and n. So let us calculate what is the expectation of r if we expand this particular formulation. So basically the term here can be, so in this particular case, if r is the number of rejectables in the sample of size n and p is the fraction rejectable, you can write r equal to np in the same way as we did d equal to n times of p dash, where p dash was the fraction rejectable. So if I substitute this value of np in this particular expression here, the expectation of r is written down as r varying between 0 and n np, and these are constants ncr p to the power of r 1 minus p to the power of n minus r. The np is taken as constant, and we have sigma r varying between 0 and n ncr p to the power of r 1 minus p to the power of n minus r. This is the fraction good, this is the fraction defective, and so obviously this whole expression here comes out to be 1, and you can say this ER as NP. For the purposes of further mathematical development, the expression for standard deviation also needs to be computed, because that is going to be sort of added on to studying this distribution further. So, for standard deviation on the binomial distribution, we can really calculate this by developing the mathematical expectation of the variance of the distribution. So, when we are talking about variance, it is basically the square of the standard deviation, and we are talking about the variation or variance of a case where we have exactly r rejectables in a sample of size n with a fraction defective p. The sample, the drawing condition, the overall lot size does not really change in this particular case. So, this can be written down as the variance of r being NP, okay, equal to the expectation of r minus NP square. Okay. So, NP being the mean r or the mean value of the binomial distribution as you had just calculated in the last step, and r is the rejectables. So, this r can vary, it can be more than the mean or less than the mean. R equal to NP is really one value of the particular distribution which is in question. So, the expectation, the average of r minus NP could be the variance of r, and so the variance of r minus NP square, I am sorry, is the variance of r. So, mean of the squares. So, if I just expand this, we get E of r square plus NP square minus twice r times of NP, and so this expectation can be actually further split apart, because this expectation in any event is a sigma, and you know that how we calculated that the expectation of r rejectables exactly is equal to NP. So, it is basically r PR r varying between 0 and n. So, for the discrete distribution. So, in a similar manner you can actually split up this function as a summation of all the individual coefficients or individual variables which are recorded in this expression within the bracket, and you can write this as expectation of r square plus expectation of NP square minus expectation of twice r NP, so on and so forth. And because they are all in any event summation. So, this is r square PR, this is n square P square PR summation, this is r NP PR summation, so on and so forth. So, let us first of all start calculating what these individual expectations are in order to find out what is the variance and subsequently what is the standard deviation in this particular case. So, when we talk about the expectation of n square P square, so obviously this means r varying between 0 and n square P square times of the probability of having exactly r rejectables. So, this comes out to be simply n square P square, because obviously the overall summation of having 0 or n rejectables in a lot or sample of n is exactly summation of PRs, that is probability of 0 rejectable, 1 rejectable, 2 rejectable, so on up to n rejectables. So, that is definitely 1. In a similar manner, if we try to calculate the expectation of twice r n p, we can represent this as twice n p sigma r varying between 0 and n r p r. So, this we already know as n p from our past derivation about the mean, which is actually again assuming that there are about p percentage rejects in a sample of n, where n p is equal to r, as we had done exactly in a similar manner for the mean of the probability distribution in the earlier slide. So, this becomes twice n square p square. So, now the task that is there is to really be able to calculate the E r square, the expectation of r square. So far whatever we have done results in a total variance of r which is equal to expectation of r square plus n square p square minus twice n square p square, which is actually expectation of r square minus n square p square. So, that is how the final variance of r would be calculated. Let us now talk about how to find out the expectation of r square. So, I am going to write down r square in a little different manner here. So, you can write it as expectation of r times r minus 1 plus r. So, essentially you are adding and subtracting r to the term r square here, and so therefore in a similar manner or in a similar logic you can write this as a summation of the expectation of r into r minus 1 plus the expectation of r. This already we know is n p from our earlier statement on means. We need to calculate what this is, and for doing that let us actually expand the formulation. So, the expectation of r times r minus 1 it can be written down as sigma r varying between 0 to n r times r minus 1 times of the probability of r. And if I may recall, this probability of r is further recorded as NCR p to the power of r, where p is the percentage defective, times 1 minus p to the power of n minus r. Just putting out the binomial distribution for r rejectables in n sample size of n, which is the probability of getting r rejectables exactly in a binomial distribution. So, we can write this down further or expand this further as sigma r varying between 0 and n r times of r minus 1 times of n c r p to the power of r 1 minus p to the power of n minus r. So, this form can be slightly algebraically manipulated here. I can write r minus 1 and then I can write this as factorial n by factorial r times of factorial n minus r, and further p to the power of r 1 minus p to the power of n minus r. So, we have to do a small trick here. We basically try to remove r and r minus 1 terms from this r factorial. So, let me just write it down in a appropriate manner as sigma r varying between 0 and n r times r minus 1 times of, let us write n times of n minus 1 times of n minus 2 factorial, which we can very well write, times of r times of r minus 1 times of r minus 2 factorial, and this we can write down as n minus 2 minus r minus 2. It really does not matter because we have added and subtracted 2 in the process, and this can be recorded as n minus r, and this further can be expanded as p square times of p r minus 2 and 1 minus p times of again n minus 2 minus r minus 2. So, I am just trying to write it down in an algebraically correct manner, but what in the process we are doing is very interesting, that these r minus 1 get cancelled in the, they are same in the numerator and denominator, and we are left with a situation where we can say that this is equal to r varying between sigma r varying between 0 and n times of n minus 1 times of square of p times of this whole term here, which is sigma n minus 2 divided by, or factorial n minus 2 divided by factorial r minus 2 divided by again factorial n minus 2 minus r minus 2 times of p to the power of r minus 2 1 minus p to the power of n minus 2 minus r minus 2 again. So, this comes out to be equal to sigma r varying between 0 and n minus 1 square of p, and we can write this whole expression here under this third bracket as the probability or the distribution whose generic term can be represented as n minus 2 c r minus 2 p to the power of r minus 2 1 minus p to the power of n minus 2 minus r minus 2. So, straightforward, this whole term n minus 1 p square can come out the sigma. So, you can record this as n times of n minus 1 time of square of p times of sigma r varying between. Now, here is a very important issue that I would like to address. Corresponding to r equal to 0 and r equal to 1, this whole expectation of r into r minus 1 seems to be 0, okay, because there is r into r minus 1 term here. So, I can say that r varies from 2 and n minus 2 c r minus 2 p to the power of r minus 2 times of 1 minus p to the power of n minus 2 minus r minus 2. So, this is nothing but 1, because this actually is a representation of p plus 1 minus p to the power of n minus 2. So, that is how you represent these distributions, and obviously this becomes equal to 1. So, I can say that the expectation of r times of r minus 1, which you started deriving in this particular step, happens to be n times of n minus 1 times of square of p. And so, the expectation of r square, which was really the expectation of summation r times r minus 1 as calculated above here plus r, is basically n times of n minus 1 p square plus the expectation of r, which is n p. So, if I further calculate this, this becomes n square p square minus n p square plus, and that is what the expectation of r square is. So, finally, let me just recall, go one slide back and see what had been left over here. So, we have already computed n square p square expectation and twice r n p expectation, and these values come out to be n square p square and twice n square p square. And finally, we had the expectation of this whole term r minus n p whole square, which is actually the variance of r, was expectation of r square minus n square p square. So, from this value right about here, I would like to plug in and calculate what is the variance of r, that is expectation of r minus n p square, and we find out that this variance can be expectation of square of r plus or minus n square p square, which can further be, which is n square p square minus n p square plus n p minus of n square p square again as applied by this term. So, the n square p squares cancel each other and we are left with n p times of 1 minus p. So, the standard deviation of number of rejectables r, which is equal to n p, p being the fraction defect, can be given as root of n times of the fraction defective times of fraction good. That is how you calculate the standard deviation of a binomial distribution. So, if we are talking about a case where, let us say, you had a variable which related to the term p itself, p being equal to the number of rejectables by n, and you wanted to calculate the mean and the sigma, that means the standard mathematical expectation of mu or mu p, mathematical expectation of p, as well as the sigma of p, this would be written down as simply p, that is 1 by n times of the expectation of r, which is np, and the variance in the same manner can be written down as p times of 1 minus p by n. And I would really like to leave it to the audience to prove for themselves using the similar algorithm or the similar approach as has been used in the case of this expectation of r or variance of r. So that is about it. So it is about more or less about how a binomial distribution can be understood or determined, and how you can predict the mathematical mean as well as the variance of such a distribution. I would like to look at some of the distributions which naturally occur, and let us also look at some cases where data has been recorded in a manner which can be applied to some of these distributions. And obviously binomial is only one case of it. There are many other distributions which can be fitted into such data. One of them is called the Poisson's distribution, another is also known as the normal distribution. And we will try to see what are the subtle differences in the data from which we can identify really whether this data would be more suited for a Poisson's distribution or a binomial distribution. Obviously the acceptance sampling and the fraction reject, whenever these terms come into picture, you would kind of envision yourself to be with the binomial distribution to force fit such a case, as you have seen repeatedly in the examples which have been done in the last about 2 or 3 modules. Now let us look at some more realistic data and see how this data can be utilized. But just before going to that, I would just like to point one more example or one more case where I would show that if we really calculated the average or the mean or the standard deviation in a normal manner and did it through the binomial distribution, would it really converge, or is there some difference? So let us look at this particular case here, where we are talking about number of non-confirming items to be 4, 3, 2 and 1 and 0, and the frequency at which this occur, that in a particular draw of 4 you could either have all 4 good or 3 good 1 defective, 2 good 2 defective, 1 good 3 defective, or 0 good and all 4 defective. So the cases that have happened for a total 40 number of draws of this case are recorded, and the frequency table here shows that at least 3 draws have come out with all 4 goods, or at least 7 draws have come out in this 40 with all draws having 3 defectives and 1 good, and similarly 9 draws have come out with 2 defectives and 2 good, or 16 draws have come out with only 1 defective and 3 goods, and similarly 5 draws have come out with 0 defectives and all good items. So if I wanted to just calculate the binomial, the mu as well as the sigma for this particular distribution, obviously it is something like a frequency distribution, and you can calculate it using normal formulation as has been earlier taught. The average comes out to be 1.675 and the standard deviation comes out to be 1.127. Whereas if we use the binomial distribution and the expected mean and expected variance, the mu p here would record as 1.7034 and the sigma np here would record as 1.189 by means that have been shown here, np and np 1 minus p, as I have just described before. And what I would like to say, if this n becomes larger, there is a slow convergence of these two, standard deviation as well as the mean calculated through the mathematical expectation method as has been done before, with the actual means and standard deviations calculated with frequency analysis. So basically if the sample size is very large, then there would be a general convergence of the mean and the standard deviation of a normal of a binomial distribution to the actual average and actual standard deviation of the distribution. Although in this particular case the values seem to be very close, so 40 is really a good sample size for. So basically you are drawing, every time you are drawing 4 pieces, and there are 40 such trials that you have made, and basically you have drawn 160 items from a lot which is otherwise. So in this particular case we are probably talking about 160 samples drawn from close to 950 overall population size with an acceptance rate of, so these 160 samples that you are drawing from 950 is the overall statistics, acceptance rate is about 17%. So basically 0.17 is P and 0.83 is the 1 minus P or percentage good. And so in this manner you can see that the mu P and sigma n P are quite close to the actual averages and the standard deviations which are calculated by the other frequency method. So I think I will close this module in the interest of time, but in the next module we will now try to force fit a Poisson's distribution and also a normal distribution to certain situations where we will first of all understand in a case study manner what are those criterias in a particular data which you would needing to know, which would be needing to know to predict whether you are going to do we are going to use a Poisson's distribution or you are going to use a normal distribution. So that we will do and cover in the next module. Thank you so much.